The speakers take their duty. We're going to have Gilles first, from Oraclize, from iEx.ec, sorry. Then Golem, and then Oraclize, and finally decentralized sports. We are selling just wonderful t-shirts if you want to buy one. If you want to support Asset, you can also become a member of Asset and check out the link on the meetup. And I see a lot of faces here that I know have been attending to our meetup this week. We had a tremendous time, we had a lot of fun, and I hope we will continue enjoying this wonderful week with us in Paris tomorrow and the day after. Please, Gilles, if you want to hear.
Thank you very much for So thank you for the invitation. Thanks for organizing this meetup. So the talk today is going to be about iEx.ec. iEx.ec, it's a project of building a distributed cloud using the Ethereum blockchain. It has been introduced already at DevCon 2 in September. And what I'm going to present you now is a sort of update of what we have been doing for the past months. So my name is Gilles Fredac, I'm a researcher at INRIA, which is the French National Research Institute for Computer Science, and co-founder of iEx.ec. But this is really a teamwork, and actually many members from the team are here. So we have Hamid, Mehdi, Julien, and Oleg. So the idea of iEx.ec is to build a distributed cloud using the Ethereum blockchain to organize a global market. So imagine a kind of Airbnb for computing resources. So computing resources will mean servers, datasets, applications, and all those computing resources will be able to advertise themselves using smart contracts deployed on the Ethereum blockchain. And then you have users can be applications, of course. And when they want to execute an application, they would go on the Ethereum on the blockchain, provision the computing resources using the smart contracts, and then iEx.ec takes care of provisioning the resource, deploying the applications, deploying the data, executing the computations, and moving the data back to the users. And so that's interesting because we're going to build, we hope, a new kind of cloud, which is going to be decentralized, so very different than the existing cloud, such as it exists now. And we hope that it's going to be low-cost, secure, and also scalable. And so I'm going to give you a brief overview of what we're trying to achieve. So first question is for what kind of application? Is it going to be the same kind of application that run now on the cloud? I think no. So we distinguish three categories of application for which we think that we are really a good solution. The first one are the dApps, what we call dApps. It's those distributed applications running on the Ethereum blockchain. So typically when you deploy a smart contract, you know that you have very limited capacity to execute your code. You have a very small amount of storage and very limited capacity in computing power. So what iEx.ec does in this case is to provide those dApps and access to off-chain computing resources so that they can have more data, more computing power. This is the first category. Second one is what I call the legacy application. These are all the applications that exist now, and we think they will move to this new form of cloud because we can provide cheaper resources. And typically it's all the applications that belong to HPC, high performance computing, big data. This is like simulations, 3D rendering, etc. And then more interesting, I think, it's really the target at the end. It's all what I call the emerging distributed applications. So these are the applications for which the centralized cloud, as it exists now, is a bottleneck. So think of everything which is like IoT, the IoT that generates a lot of data. So you don't want the data to move, up to the cloud and going back to the producer or the consumer. So in this case, you need a new form of infrastructure, and you need something which is much more decentralized. So maybe you have heard the term of fog computing or edge computing. So here, the decentralized cloud is something quite similar to this kind of infrastructure. So an interesting thing is so here in this picture, what you see is the different sort of resources So here, what you see in this figure, it's all the different kind of resources that we are going to have in the iEx.ec distributed cloud, and that's quite interesting. So on my left, you have the GPU mining farm. So it's interesting because those machines are quite similar to somehow to supercomputer. It has some supercomputing capabilities. So they are very powerful, they consume a lot of energy. And for instance, this year we were at supercomputing, as he says, and I think it's the first time where we had this discussion with people doing HPC to see how such kind of mining farms could be useful for running like deep learning and kind of applications. We are working also with people doing distributed data centers. So distributed data centers is a kind of trend, an emerging technology. The idea is to move the server out of the walls of the data center. So for instance, kernel computing, Steamergy, these are two startups, French startups, but they are the similar one in Germany, I know. And for instance, Steamergy, what they do is that they have, so this is a furnace, it warms the water before being distributed in the building, and actually this is the heat generated by the processor that warms the water. Kernel, what they do is, this is a heater, okay, so it's located, the server is located in the apartment, and it's the heat generated by the processors that is warming the apartment. So these are good examples of distributed data center. And finally, the last element, this is something we are developing now in collaboration with some colleagues from Tunisia. This is what we call the energy positive worker. So this is a very small device. It has a battery, a solar panel, and a Tigra or ARM processor, so it does not consume any energy. And the interesting thing is that all these resources will be able, you can provision all these kind of resources within the same market. So that's very interesting. And this is what I think is quite new in the distributed cloud. And I call that ultra-scalable system because you can scale your infrastructure according to different criteria. That can be performance, okay, like in HPC classically, or that can be cost, like in the cloud, or you can also imagine several criteria like power and energy and these kind of things. So the way we're doing iEx.ec actually is that we are leveraging technologies that we have developed as a researcher, and we call that desktop-grade computing. It's maybe something you know under the name of volunteer computing. So desktop-grade, it's the idea of using idle PCs distributed on the internet to execute a large application. And maybe you have heard of a project like SETI at Home, for instance. So this might sound a little bit exotic, but this is actually a very mature technology. It has a lot of features already. It's very well established. In particular, we have participated to various European projects where we have actually deployed real infrastructure executing real science based on this technology. And here for this project, iEx.ec, we are relying on ExtremeWeb HEP, which is developed by Oleg Landryjowski, who is a researcher at the National Research Institute for Nuclear and Particle Physics. And what's interesting is that you can basically have a lot of the features that we need to do in iEx.ec. It has all the features, so it's called ExtremeWeb, but of course, what we have to do is to bridge this infrastructure with the blockchains. Okay? And so what we have done for the past months is to build a sort of proof of concept so that we are sure that any distributed application, any dApps, would actually be able to use those computing resources provided by the distributed cloud. Okay, so in the past months, we have designed, it's a toy application, I will describe it later, but it contains all the elements that you can find in a Ethereum application. So you typically have the front end, you interact with MetaMask, could be another kind of wallet, it doesn't matter, with the blockchain. And what we have built is this sort of oracle that allows the computation to be offloaded to the decentralized cloud. So the application we choose for that is it's a vanity generation. So I don't know if you know what is a vanity address. It's a Bitcoin address that for which it starts with a specified pattern. So the pattern won't, the user wants a specific pattern, and then we will try to find an address that matches. This is something you can try. So the interesting thing with this application is that first it's very simple, but still it has very good properties. First, it's too intensive to run on-chain. You can put that using a smart contract. It would be too costly to execute on the Ethereum virtual machine, so you have to go off-chain to execute this application. It's parallel, but it's totally trivial to parallelize, but you just want to execute the task. But the interesting thing is that even though it's very simple, it's a common pattern that we may find for various related crypto issues. For instance, for people doing relay for several, maybe Jérôme who told me about relay, it's the same kind of pattern. People doing homomorphic computing, this sort of thing. They have to go off-chain. They would like to do it for their smart contract, but they need to go off-chain. So here is a little sketch of what's going on. So we have the user that interacts with the front end, the Ethereum blockchain, and the things that are done off-chain using iEx.ec. Okay? And so we have, first we have designed a token, which is exactly compliant with ERC20 tokens, the regular one. And so people first get this token, then use the token to buy the execution of a task. It goes to a specific website which is called Bitaddress that allows you to generate your own public and private key so that the generation of the vanity is fully secure. And then there is a smart contract that describes this vanity task. Okay? And when the user provisions the token for the execution of the task, or Oracle is able to monitor this, observe that the token has been spent, and then execute the task accordingly. And at the end, we fetch the result back to the user. So the network we have used for testing this, so you can see a plot of the network. It's basically relying on the Grid 5000 infrastructure, which is infrastructure for research in distributed system. So you can see that we have used that since actually November. We have used up to 2,000 machines, 3,000 machines. So it's basically to test the reliability and scalability of the system. And also we're using the Steamergy server. So this is the server that you see here that are the kernels. Okay, so conclusion. This is iEx, it's a distributed cloud. It allows to do off-chain computation or blockchain-based application. It uses the Ethereum to create a market network for computing resources. We have a roadmap. We invite you to join our project if you are interested, if you are a developer, if you are just curious. We have released a white paper already to describe the technology, the roadmap. We're going also to release our token very soon. So if you're interested, join our Slack and talk with us. Thank you very much.
So we're going to take a question after the presentation, so we can do it live. So I invite so now Golem for the Golem product solution. Now we're going to take a question after, so when everyone is done, we can switch to the panel discussion.
Hi, I'm Grzegorz from Golem, and in few words I would like to introduce myself. So, for 15 years I was the researcher and scientist at was University of Technology, mainly working with machine learning, data mining, logic synthesis. But recently I met wonderful people from Golem and decided to move from the university to this business. So today I would like to say a few words about Golem. And first, let me say about computation and how they look in past. So, in the 60s, we developed mainframes. IBM developed these powerful machines, and these machines are used until today. The main advantage of these machines is that they has the possibility to do a lot of transactions in parallel. For example, we do payments with credit cards. We know data centers with powerful servers. We also do a lot of computations using our personal computers and laptops. And recently, we also developed cloud. For more specific issues, we use GPUs and FPGAs, generally for teaching neural networks, or for example, if you would like to mine another prime number, we use FPGAs. So different ways of high performance computing. And there are few disadvantages of these technologies. For example, these technologies are expensive. Usually there is a central unit and a lot of computational power is wasted. And to somehow challenge these problems, we develop a disruptive technology called Golem. So, computers are like cars. The lifetime includes more than 90% of they are stacked on the car parks. The same is with our computers. How many of you now use your computer? We do not use the computer during night, during computing to the work, during meetups. So we try to utilize this computational power in Golem. So we try to connect them and make a Golem network. However, what I would like to note, this computational power is very different from digital circuits. Scientists try to minimize the distance between transistors because of the communication between nodes. Cloud or Golem network is for different approaches. So when the task, we can split the task in separate independent parts. It is the best use case for such solutions. So how does Golem look like, and who will benefit from this technology? So we have providers. Everybody here can be a provider. Everybody can provide the computational power by using his computer. The requester benefit from using the application, and software developer can benefit from implementation on the Golem network. How does it work and how it was built? So we use virtual machines to implement nodes. So Golem is exactly the network of virtual machines. And to decentralize this network, we use Ethereum. For payments, we developed GNT currency. Typical use case are rendering, and we have a few milestones. So in the first one, we mainly focus on rendering. However, as I said before, the typical use case is Hadoop system. So we would like to implement Apache Spark, and later Julia language, Caffe, it's a framework for neural networks, TensorFlow, and other software which will be provided by software developers. So it is our timeline. So we would like to develop the complete Golem in 4 milestones. The first one we would like to finish in May, and it will implement basic stuff, including the first use case, rendering. The other programs, more advanced, like reputation system, verification, we implement in subsequent steps. Here's our group. We're still recruiting, so if anybody would like to join, please check on our website. There is information provided, so you are welcome to join our group. Here's the contact email. Thank you very much.
So, Thomas, please. Thomas, the planning, so Oraclize.
Good evening to everyone, and thank you for having me here. I'm Thomas Bertani from Oraclize. So during this presentation, I will try to show you what we call the computation data source. So this is something very different compared to the other 2 presentations we have seen so far. So first of all, just a couple of slides to introduce Oraclize to those of you that are not aware of what we are doing. So essentially, Oraclize is a system which is trying to provide data to the blockchain, separating data sources, so the owners of data, from the party in charge of pushing transactions to the network. So essentially, as you can see here, we are agnostic to the blockchain. So most of our clients at the moment are using the Ethereum integration, but we have different integrations even with Bitcoin, Rootstock, and iEx. There are others coming as well. So we are trying to stay agnostic because we see the value of our engine, so for Oraclize, even outside of the blockchain context. So of course we love the blockchain, and we're in our team as at the moment 25 years cumulative of blockchain experience. So all of us started working in this space in 2012, 13. And we have designed a way to provide secure data from data sources, so from any web API, with no need for them to adapt to the blockchain. And for those of you, I think 99% at least, who will be attending EdCon, there will be a presentation specifically on that on day 2. So at the moment, we are providing pretty much the most widely used Oracle system on Ethereum, and we have sent since September 2015 1.5% of all Ethereum transactions ever to feed data to contracts. So I don't want to spend too much time to talk about Oraclize, but what I want you to see here is that the way Oraclize works is via asynchronous transactions. So essentially, there are 2 transactions. The first one is a smart contract calling out to Oraclize for ask for some data, and the second transaction is Oraclize sending back the data to the contract. So when you query Oraclize for some content, for some data, you have to specify essentially 2 things. The first one is the data source, and the second one is the query. So the data source can be pretty much anything, and it's the context. So it can be URL, meaning that you will query a web API. It could be some specific API like Wolfram Alpha. It could maybe be Vitalik if he starts to provide this as a service via Oraclize. And it can be many different things. So for example, we have recent integrations with IPFS and with Swarm. So you can actually fetch some context from those two distributed networks straight from Solidity code. Today I want to specifically focus on the computation data source. So the computation data source is something which is available in Oraclize right now and which is being used already by some banks and insurance companies. So this has been audited for a while, for over 6 months now. And those companies are using it, but we didn't release it to the community earlier because essentially it's very complicated. And today I will try, so let's hope you can appreciate it and understand what is the use case. So I'm really excited to try to understand what the community could use this thing for. So any feedback would be greatly appreciated. Essentially what we want to solve in general is limitations of the blockchain. So the two presentations we have seen so far try to address something super exciting, which is high performance computing, supercomputing, and so on. So we were listening to things like trying to find Bitcoin vanity addresses or trying to do some complex rendering. But the reality is that on Ethereum, we are very limited from the Ethereum virtual machine. So there is a huge gap between the capabilities of the EVM and supercomputing. So we don't really need a supercomputer for most of the tasks that we cannot do on the EVM. So these are the limitations of the EVM. So we have essentially some constraints given by the architecture, like the fact that we cannot have floating point arithmetic. So in practice, this means that you cannot run a derivative on the blockchain, for example, because there is no way to execute complex math on the blockchain. Then we have other limitations, for example, the fact that many functions are not available there because we don't have precompiles, we don't have opcodes. Think about very simple RSA signature verification, so SHA-1 or many other functions. They are simply not doable on the blockchain. Even ZK, Snark, and many others will be doable after the hard fork if we can make to put the precompiling there. But of course, it's not that trivial. Then we have the gas limit. So we know that even if the block was full because of some complex computation, well, by spending $1 we can probably, today at least, we can probably fit one transaction which will probably execute some part of our computation. So it's not that attractive for the functionality that are not embedded natively into the EVM. So we have high costs, which are not always a good fit for what we want to do. So let's say you want to verify an RSA signature coming from your national ID card because you want to identify yourself to a smart contract. Well, today you can maybe do it if somebody is willing to write some thousands of lines of code and then willing to pay maybe $10 and fill 10 consecutive blocks, then maybe you can do it, but it's not that attractive. And of course, if you want to use major libraries like financial libraries and so on, you simply cannot use them because they are not written for Solidity and so on. Also, you don't have confidentiality, privacy, scalability is an issue, not because the network is badly designed, but because any distributed system is inherently difficult to scale for the way it works. So what we want is to overcome these limits, possibly without filling the blockchain with useless stuff. We want it to be cost effective in some ways, to some extent at least, and we want to keep the system transparent, right? So we don't want to break the old security model of the blockchain. And we don't really want to execute code on every machine, because this will just be a different blockchain, probably, or a different distributed system with the same limitations. So it's pointless. And in most cases, even running the same code on different machine doesn't lead to a consensus. So think about if we want to compute a random number. If all of us now will try to, I don't know, think of a number between 1 and 100, I think that we will never find a consensus, right? Because everybody will have a different outcome. So this is one solution, it's the computation data source. So this is the step one. Please try to bear with me. It's quite technical, but it's not too complicated. So if you're a developer, I think that it should be pretty easy to understand how it works. So first of all, sorry, but Docker is shit. So Docker doesn't really provide installation. It's really bad, and it opens a lot of attack vectors, and the attack surface is huge. So you don't really want to use Docker for installation. And the reason why we are using it here is just because it pretty much a lot of people know how to use it, and it's pretty good to define a RC for what you want to execute. So it's good to define like the context of the execution. So here you define the context of the execution. In this case, you see that it's just 5 lines, pretty easy. We just say that we want to start from a base image based on Ubuntu. We want to install Python and to execute a 1 line of code, saying to print a random number between 0 and 100, right? So this is the first step. So you create this in your local machine. Sorry for the resolution, but essentially you put the Docker file and any other file dependency that you might have into a zip archive, and you put this archive over IPFS on your local node. Then you have to take care by yourself to upload this file and to keep it there on IPFS, so you can have an always running node, or you can hope that some other nodes will preserve your file for some reason. So in our case, you see that our multi-hash on IPFS is QM and blah blah. So this is the way you use it. You can actually test it out now because it's live, as I said. So we also have a browser security integration. So if you copy the URL on the top, you can test it straight away from your laptop in memory without having to initialize any testnet or anything like that. So the code is pretty simple, and you see that we just call Oraclize with Oraclize query, specifying that the data source is computation and the query is the hash of our code, right? So this is essentially unique representation of our zip archive. So if you have access to IPFS, by looking at the smart contract, you can see what code it is referring to, right? And then we get the callback with the result, and along with the authenticity proof. So we come to this in a bit. And you can do whatever you want with the result. So this is a typical use case. There are many reasons why you want to use something like this. So you could delegate RSA signature verification, you could delegate whatever code you want, a financial library. It doesn't even need to be open source if you don't want to. It can be a binary, it can be anything, right? And you get back the result as we have said. So with that code, I've run this like 2 hours before the presentation. So you see that the result was 46. And we have saved it in storage and blah blah. Well, for those of you who know how Oraclize works, so this is pretty much the same. So we provide this authenticity proof in a way which can be persistent, and you can verify the authenticity proofs to know that Oraclize didn't tamper with the data. So in that case, with the computation data source, we are initializing a custom environment which is provably safe. So essentially, it's a fully locked down instance run on Amazon Web Service at the moment, and you can verify that Oraclize has no way to tamper with the result of the machine. So if the result is wrong, pretty much you have a 100% guarantee that some employees at Amazon did tamper with the physical machine, right? So this is not perfect, but the amount of trust can be lowered a lot as soon as we support other cloud providers. So of course, having few semi-trusted, non-anonymous attestators like Amazon and Google is much safer than having 5 random people in this room, because essentially the reputation that Amazon and Google have at stake is much bigger than anybody of us. With the authenticity proof, we have a cryptographic proof showing that those actors did behave dishonestly. So, in a nutshell, this is working today, so you can use it. It's provably safe off-chain context, so I just have 10 minutes, and I think that I've already spent more. So if you have questions specifically on that, please ask during the panel or whenever you want. I will be around even during the weekend. So Docker is just used to describe the content, but the instance where this thing is run is a throwaway. So it's fully insulated. Even if you break it, it doesn't matter, you don't really harm anybody. And it has a very broad applicability. So there are many use cases where you want to use this today on Ethereum, because the application you would like to run is not capable to fully run on the blockchain. So you need to move it outside. Of course, if you have native operators, it doesn't make any sense to lower the trust involved. But in some cases, you don't have any choice. So it's a layer 2 solution. It's fully auditable, scalable, and so on. Thank you for the attention.
So Clément Lesage from Decentralized Codes.
Hi everyone. So I will also be talking about how to solve the problem of having such a small gas limit when we want to execute computation in smart contracts. I made some simple program just counting 1, 2, 3, and at 60,000 it stopped because of the gas limit. I've done even more, asking the program on the EVM to save the result, and it stopped at 200, which is what you could do as a human writing on a sheet of paper in about 4 minutes. So we have about the same capability on the EVM that we will have as a human, the same order of magnitude. And this is not interesting because if I have a computer, I want the computer to be better than myself in computing. So to solve this issue, the first idea is that you don't compute everything in the blockchain. You just use the blockchain to verify the computation. So, for example, we want to know if there is a path of length stance in this graph. If we do it on the blockchain, we'll have something quadratic. We'll use the shortest path algorithm. But this part of the algorithm, we can do it off-chain and just use the chain as a verifier. We present on the blockchain the path. We compute the total length of the path on the blockchain, and we can do that in linear time. We have some theoretical framework to study those cases, which are also Merlin games. So we have Merlin, which is a user with a laptop, nice laptop, or even a cluster sometimes, with a lot of computational power. And Arthur, which is really limited in computational power, but which is interesting is that it can throw public license. Even taking the block hash is not perfect, but in this protocol you don't really mind the randomness is not perfect. It's still working. So we want to design protocols that Merlin can propose to Arthur. And I'll just give you, before a really simple example, where we have Merlin finding a path and Arthur verifying the path. So let's go back to, I think you've seen NP and some computational theory. And in NP, every answer can be verified, every guess answer can be verified in equal minimal time, even if it may take way more time to compute. But in practice, users also have some computational limitation. Here I gave you a simple example, but I have way more complex example, which will include reversing hash function and stuff like that, and actually you won't be able to do that, even on your cluster. And even polynomial time tends to be too high for the gas limit. So we have to find another model to get the result of computationally intensive tasks in the blockchain. And this new model is to use the blockchain as a computational court, where different users will provide evidence of computational results. So let's take, for example, a well-known problem, which is a knapsack problem. You have a knapsack, you have an item with value and with weight, and you want to put the highest amount of value in the knapsack while having the weight below the capacity of the knapsack. So you do that, you compute off-chain, which is proportional to the number of items and the capacity of the knapsack, which is still in NP complete, because the capacity is exponential to its representation. And you put the result on-chain. And if someone put a wrong result, it won't be a problem, because on-chain you just take the highest value from. And so you just have someone to put the wrong result, to have someone to put the right result, to have the right result on-chain. In some cases, you will also need to disprove wrong result put by other people. For example, here it's a matrix multiplication. The first one gives the right result, the second one gives a wrong result. And you're going to disprove this result by simply exhibiting the cell 99, which is false, and just exhibiting this cell and finding the value of this cell in just linear time. So it does not take a lot of time with the blockchain, and all the hard computation you've done it outside the blockchain. So you may ask, okay, I gave you example, but what if I have a problem which is absolutely completely different from what you've shown? So we have a scheme for general computation on the blockchain, to have the result on the blockchain. So everyone will be able to submit the result with a deposit to avoid people making frivolous computational claims. And you will disprove wrong result with interactive verification. So let's assume we are still using the simple program, just counting 1, etc. I'm a left party, I've counted up to 17, and I put 17 on the blockchain. But someone dishonest put 35. How do I show that this computation result is false? So the idea is that we go at the medium computational step, which is the 9th, and we ask what is the result of the 9th step. And the malicious guy says 27. But this way we know that he has made the mistake before the 9th step. So we just have divided our search space by 2. So now we're searching between 0 and 9. And so we ask what's the result in 4? And we say 4, so 4 is right. So now we know that the mistake is between 4 and 9. We ask 6. 6 is giving us 24, which is false. So we know the mistake is in the 4 and 6. We ask the 5th. We say it's 5, so 5 is okay. But here we just show the transition. 5 plus 1 is 6, and now 24. And so we've disproven the result. And we've done that in logarithmic time, which means even if the computation takes an enormous amount of time, it's still really short to verify on the blockchain. In this model, we just need to verify when someone is trying to cheat. So in most of the cases, you will just have one honest guy putting the right result on the blockchain, and no one will complain. A nice property is that you have the right result as long as you have at least one honest party. What we have to be careful of is to deal with timers. Like if I ask some value and the other guy is not answering, what do? Well, we have to put to set that this result is wrong. So we must deal with blockchain latency, and we already have to have some computer be ready to answer to some computational challenge. Now let's use both parts. The first one, the verification part, and the code. With the verification part, we've seen that we can have everything verified in polynomial time in case of yes instance in NP. And in the second part, we've seen that we can have interactive verification in logarithmic time. And the logarithm of the polynomial is still a logarithm, which means that you can verify every result in NP in logarithmic time on the blockchain. So what's for? Well, I run into this matter of gas limit while trying to build a complex computation system for my project, the decentralized court. I also run into this problem when trying to put advanced voting method on the blockchain, the truth method, which is you wrong proposition instead of just voting for one proposition, which give you more middle proposition and is less prone to strategic voting. But you can go even further. We can use machine learning on the blockchain. We could even have an AI learning on the blockchain, paying people to do computation. And if at least one party is doing the computation right, the AI will have the right answer and will be able to take decision without being dependent on any computer, on anyone, and living on the blockchain as an economical entity. So thanks for listening. I'm mostly working on the decentralized pool project, the Clear, which is not what I presented, but it's what I presented was some step I needed to design a nice computational system, a nice core system. You can find me here, and I'm also done with some freelancing, mostly in security, but if you also have some computational nice problem, this might interest me. Thank you for listening.
So I guess now we have questions. Who want to start? Can I say anything to our nice speakers? Yes, no? Yeah.
Okay, thank you. That's a question for Clément. I guess as a use case, what I would see is also complex optimization problems, because then you would have various computers trying to find the optimum, and obviously the one that finds, let's say, the minimum for a problem would win. So how have you thought about that?
So exactly, I've shown you a knapsack problem, which is in fact an optimization problem. And in case of optimization problems, how to do that is quite straightforward. You let everyone to give a point in your optimization problem. You compute the value you want to optimize on the blockchain, and at the end you just take the best value which has been exhibited on the blockchain. So I think it's the easiest use case. You can do that in one day, but
okay, thanks.
The last example is quite hard to implement.
Someone else?
Yep.
Thank you. I have a question for Thomas. You spoke about confidentiality and privacy of computation, and I would like to understand in your example how to make the Docker file private, and maybe not an IPFS, but I want to understand. I don't know if it's possible.
Thank you for the question. So I think I don't need the mic. So essentially there are two parts for the confidentiality. As for the confidentiality, the first one is the one you have mentioned, which is how do we keep the Docker file or the zip archive in general secret if I want to. Well, the point is that in the presentation I showed you IPFS, but actually this is an optional part. So what you can do instead of putting the IPFS multi-hash is just putting the SHA-256 of the package, and then you can send straight to the initialized instance the package for the execution. So this means that the package doesn't need to be encrypted because it's just received by the fully locked down instance, but you don't need to disclose it to the whole network unless you want to. And you can even disclose it just to some interested parties, for example, because they can verify that the hash on the blockchain does match with the archive, and the instance can verify it as well, but Oraclize and the rest of the network are not seeing the actual code which is being executed. So this is one part. The other part is that, for example, you might want the instance to be able to decrypt some text, for example, or some private information that you are sending. And one way you could do that, of course, is not putting the private key in the archive, because everybody will be able to see it. But you could, for example, have a very simple code which listens on a socket, which maybe is authenticated. There could be different ways to prevent abuses. But essentially, you want the instance to be able to receive from some trusted source a private key, so that then it can decrypt some very specific messages. Does that make sense?
Well, essentially just a short comment. Thomas mentioned that you can either put your hash on IPFS and run, or hope someone takes it. I just thought, well, Alexandria library might be a good thing, because it's just a little incentive mechanism on top of IPFS. So you don't have to hope someone takes it. You just pay them. That's it.
What is the library that you mentioned?
Alexandria library. The guys using IPFS and some Florian coin blockchain to just incentivize people to take your IPFS.
Ah, okay, so this is like an alternative to Filecoin which actually exists?
Sorry?
This is an alternative to Filecoin protocol?
It exists, it's working. I mean, for this case, it's actually, yeah, it will work.
Thank you. An alternative one day probably will be Venezuela, once the incentive mechanism will be there.
Yeah, the lights go down. Someone else? I think I don't need the mic anymore. Yeah, please.
Okay, so I'm presuming this would be applicable to iEx.ec, Golem, as well as Oraclize, potentially a decentralized code as well. So the question is, if a user sends, if a user sends malicious code, if they upload malicious code to be run on the machines, what's the implication of that with your specific protocol, and what are the safeguards against it, against somebody potentially taking control of the machine through privilege escalation of Docker, or however the file will be run. So I guess if you guys want to go in order, or however.
So the way we deal with this usually is to use sandboxing techniques. So sandboxing technique, this is the idea of you try to isolate the execution of the remote and the code execution on the machine. So there are several ways to do that. We started to do that a long time ago by inserting module and trapping the source code, and we used exploit a long time ago. Then later came virtualization, and now there are containers. I don't think that containers are good for that because you are sharing the Linux kernel. This is something you want to do. You can do that by just using the virtualization, and then you try to block everything down so you don't. You're not allowing network access. You're not allowing access to the host system. But it's not fully. There are attacks that allows you to be very yeah,
so it's very similar. As I said during presentation, we made Golem on virtual machines just to separate the machine of the provider from the requester system. So the requester system is somehow sandboxed. That's why it is separated from the system of the provider.
So you're saying there's no chance for a privilege escalation of the sandbox?
I didn't say that there's no chance. We try to do the most just to prevent before attacks.
Well, as for the computation data source, well, I've mentioned that Docker, as yesterday as well, is not that safe, and in the past we have seen different attack vectors, specifically on Docker, which could actually get root access to the machine. So this is probably not, we don't probably want to compromise the whole network. This is the reason why we are using stateless throwaway machines. So the code you can execute in the Docker and in the throwaway machine, it can pretty much do everything. So it can even fetch web resources or all this kind of stuff. But as long as the attestator infrastructure, so in that case Amazon Web Service, provides an isolation from their instances to their infrastructure, which hopefully it does, in a good way, then the authenticity proof is safe, because the authenticity proof is just collecting data from Amazon APIs, not from the instance itself. So it's just fetching information to describe the state of the instance.
And I don't know, is it applicable to decentral compute, or?
No, it's I gave an example on how to solve this issue, and you will, for some particular application, you will have a particular client executing a particular kind of compilation, but you won't ever interact with the computer because you want all the compilation to be deterministic. It's like the EVM, so you don't have any risk of privilege escalation because you can't use any system routine or any stuff which may be different from one computer to another.
I think actually if I can add something to the centralized code, well, we don't need a mic. But if I can add something very interesting, I think that decentralized code is actually a continuation, if we want, of the project that Piper Mariam started over 1 year ago, which was called the computation market. And it was similar in some ways and different in others. So it's interesting because it needs to be deterministic, right? So not all computations can work there, but some interesting computations, and a lot of them can be executed in this way. And I guess this is a question. So I wanted to know if, in your case, the code had to be submitted, like in the Piper Mariam case, in Solidity, and then it's just executed in memory of chain and challenge on chain just in case, or if in Solidity we just do the verification step, and the actual code that we want to execute is sent in some other form.
So decentralized code is not what I presented. I presented the method I investigating or my use cases. So decentralized code is not one approach, it's not a project, it's a set of methods which can be used for project which run into Gasly. If you're talking about the last example, you will use Solidity code because you want to be able to do one step in Solidity. Okay. So you want to have Solidity code for one step. And in some other cases, it's just one particular problem, so you don't even
Well, I had a question for Gilles, specifically. Do you expect a lot of miner to switch to your cloud computing solution?
I don't know if switching is a good term, because most of the miners, they usually have a mining rig is a couple of GPU cards, okay, 4, 5, 6, linked to a CPU. So switching is maybe not the term as the, because in fact we are first certainly interested in their CPU. So we could very well imagine people having mining with their GPUs and then giving us the CPU, which for us would be very interesting. Now we are also in talk with people having significant mining farms, and in this case it's very interesting because there are two supercomputing capabilities here. It's a very specific machine because those people have processors, and in the HPC area most of this time it's NVIDIA. NVIDIA has something like 98% of the market. So over all the supercomputers in the world, there is only one in China that has an AMD processor, and it's people from the AMD University, so the Army University, the people Army University of China. It's very specific.
So it would be very suited for, say, Ethereum mining rig, because the CPU is only in use when you have to compute DAG, as far as I know.
Definitely, we could use the CPU of any miners. I think so. Unless they use that for also mining the blockchain, but that doesn't make sense because it's not. So that's already a number of CPUs that we could have.
Maybe Golem could describe, Jagoshi could describe the way you use the blockchain to reward people for the computing power, for example?
We use Ethereum instead of Bitcoin, for example, because it gave us additional functionalities. For example, we can check the account state, and nodes can talk between each other. So it is the case we use Ethereum and blockchain. So there are other cases. For example, we can store historical transactions. For example, the other case is that we can do microtransactions. If you would like to do the payment using the common way, sometimes the value of the transaction is larger than the value of computation. So that's why we are all interested in microtransactions. So it could be provided by Ethereum.
Yeah, Tim.
So your solutions are all wonderful, but they could only get the full leverage if they are tightly integrated in Geth or Parity, all the Ethereum nodes, I think. How can we achieve this? Are there plans already, or?
I'm not sure if I understood your question.
Well,
Yeah.
I think that if you really want to achieve full leverage of cloud computing in Ethereum, then it must be integrated in the Ethereum nodes so that it's easy to roll out, for example, Docker system or iEx.ec and Golem. So, am I wrong?
I think that it is not completely integrated. We somehow are dependent, but it is not completely integrated with Ethereum. So I'm not sure it's answer.
I think that this is something to avoid, because if it makes sense to include it in the node logic, then why don't simply put it into the EVM? The reason why we are keeping this off-chain is exactly because we have limitation in the way decentralized networks work. So if we put them in nodes, then we come back to the exact same problem. So we want to keep things separated, and myself, I think I will stop running my nodes if the resources and all the demand will go up that much to execute any random piece of code coming from God knows who. So in Ethereum, we know that the scope of the execution on our computers is very limited, and it's limited within the boundaries of the EVM, which is very limited by design. So I think that it's correct to keep things separated.
So you are not also fan to integrate Swarm?
Right?
Swarm, you are also not fan to integrate Swarm?
I think it should be optional. So I think it should be disabled by default, and nodes could optionally enable it if they want. Because this is something else, you know. This is the same thing as Whisper. So it's correct to leave this choice up to nodes, in my opinion. So it's a different layer. It's not the Ethereum consensus layer. Whisper is a messaging system. Swarm is distributed storage, and so on. It's not the same thing. It's an additional layer which can coexist in some ways. But for example, think even about Swarm. Swarm cannot speak to the EVM. So it's something completely different. It can leverage the Ethereum blockchain, but it's layer 2 solution. It's not the same thing. So I think it should stay optional.
Any other question?
What are the difference, if any, with a project like Tendermint, which try to modularize the blockchain and separate the consensus layer, peer-to-peer layer, and the network layer from the computational layer? If you know about Tendermint enough.
Is this for me or?
No, not for you, because you, I think Oraclize is quite different. The other three, perhaps.
Well, I guess Joseph Shaw will be there with Tendermint tomorrow.
I myself, I don't know much about Tendermint, so from my understanding, it's just a permission system, right?
For the present, but
so it's based on different assumptions, and for example, the consensus mechanism is different, and the governance model is different, and it's a different context. It's not easy to compare the two things. So somebody could even claim that it's not even a blockchain.
How do we pay for each service on each of your projects?
Good question. So what we are doing is that we issue some tokens, and then when you describe the task, for a task you have someone providing the data, providing the computation, the servers, if you want, the machine, and providing the code. And so the payment is done using a token and then distributed according to those three providers. So at the moment, very simple, but of course, in the future it will evolve with different payment schemes.
So you can forecast the cost of execution of the calculation given, or you must ask the payment after the calculation. or the payment is fixed?
For the moment, we didn't go that far. At the moment, it's more or less everything is fixed.
Yeah. Okay.
How much it costs.
So if you can see the time of calculation of the task asked before.
So what we do, what we think we're going to do, is to have some sort of kind of clustering the tasks and clustering the different elements, so that you would have some sort of categories. So tasks so we would have, for instance, some machines that we can use to benchmark the application. Okay, and so the tasks are going to be, so you're going to have one task that you're going to discretize the time to execute a task on those benchmark machines. And so the price is going to be set per task execution. So we are not going to monitor the time, we're going to execute the task and put this task into a specific category and then pay according to this category. So it's not going to be super accurate, but it makes things much simpler to pay per task.
So in Golem, it depends on the task. If it is deterministic, we can start testing, initial testing, when we can check how much the whole calculation will cost. For non-deterministic, it is the consensus between provider and requester.
Oraclize is essentially, the Oraclize engine is a distributed architecture that we manage as a company. So essentially you pay per call, and since there are some boundaries, for example in the type of instance that we initiate, and there are some time restrictions, like the fact that your execution for computation needs to terminate within 10 minutes on that machine, which will be configurable, but at the moment there is this fixed restriction. You will essentially pay per call, and the price is fixed in US dollars. So the price depends on the authenticity proofs you ask, because we use dedicated trusted computing techniques, so we need different parts of the architecture depending on what authenticity proof you want. So for example, if you want the Intel SGX1, you will have a cost. If you want the one based on Qualcomm and on the Android technique, you will get another one. TLS Notary is different, and blah blah. For the average case, let's say that you want just TLS Notary and a computation which terminates within 10 minutes, it will be 50 cents flat plus 4. And of course, this is to be compared with the alternative on chain. And if you go off chain, it's probably because on chain is not feasible. And at the moment, even if it was doable in one block worth of gas is around $1 US. So it's at least twice.
So it depends on the use case. For example, in a voting system, you won't have to pay anyone, because the one with the proposal, with the winning proposal, will show the computational proof and include the computational result on the blockchain without being paid. In some of the setting, when I talk about the AI smart contract, the AI smart contract is going to pay the first person putting the right result on the blockchain.
Okay, thank you.
Yeah.
I have a question. Is yours, I guess there's 4 different systems here. Is your system permissionless in that can any system join and then perform work, execute the code, and then get rewarded for it? And then if it's permissionless, how do you choose which providers get what work when there are more, when there should be more providers than requesters?
So for iEx, we are doing a hybrid system. So we have been doing that this is because of the history of iEx. We first did, computation of the internet, but it has been actually used in the field of grid computing, where things are extremely authenticated with a lot of security. So we have this sort of hybrid model where things could be either what we call public, in this kind of sort of permissionless, or private, and in this case everything is well authenticated, secured, etc. All these kind of things. And then you can choose between, and you can define the authorization according, to if your computing resource is private, then it's going only to execute private applications. If it's public, you can it's going to execute everything, and you can set the management rights for every element in the system. So the different elements are the computations, the machines, the application, the data, and then according to it by public and private.
Well, as for Oraclize, essentially we manage our infrastructure as a service, as a company, so the engine is not open source, but all the contracts and all the specification is open source, so even the tools for the verification are open source and can be used by any other company who wants to follow the same format. So actually moving to the same service as provided by a different entity is definitely possible, and the promise of Oraclize is that if we will send a transaction back, then the result will be correct and you will be able to verify it. But of course, since we are not anonymous, if for law enforcement reasons we are forced not to send back a transaction to a contract because, for example, it's illegal, then you will not receive a transaction back. So of course there is some space to competition if you want, or to other companies providing the similar service. But as for the computation itself, it's being executed on a single instance on Amazon Web Service or other attested or other architecture. So we just initialize the context.
So of course, in all examples I've shown it's permissionless, because we want anyone to be able to put the right result or to disprove a wrong one, such that if you have at least one honest party, you have the right result. So it has to be permissionless.
Could you repeat the questions further? Is it permissionless in that anybody with a computer can join to do the work, which I guess Golem is. And in that case, how does the system choose the providers?
How does the matchmaking happen for requested computation? How do you choose
we'd like to develop the quotation system, and there will be a sequence where we choose the computers from the top to make the calculations.
I think that at the end of the day, you need to either verify the result on chain, which is not always doable, or on the other side, you need to trust somebody for the execution. And every day you're trusting Intel or AMD anyway on your CPU. And we know there are many vectors there as well. So when possible, it's definitely a good option just to keep it as a permissionless system, as you mentioned, so anybody can execute it and send back the result, and then the smart contract will verify. But it's not always possible, so think about the trivial case of the random number. How do you verify if the random number is really random? Or how do you verify the RSA signature verification? So the very reason why you went off chain is because you couldn't do it. So it's always about finding a good balance. And I think that here on stage we have 4 different projects which do address the computational problem in different ways, because essentially it's a different definition of the computational problem. So we are all trying to address different use cases, essentially.
Well, I couldn't find a better way to end this. Thank you very much, Thomas. I think we are not to leave the room in 5 minutes anyway, and so we don't get a good